Hello everyone, welcome to Neso Academy. We are implementing combinational circuits using VHDL, and in the previous few lectures we implemented the half adder by using all three modeling styles, and today we are going to implement the full adder using VHDL. So, in this lecture, we will first understand what is a full adder, then we will implement it using VHDL. So, our today's topic is full adder implementation using VHDL in Vivado. Now, the question is, if a half adder can perform addition, then why do we need a full adder? And the answer lies in the limitation of the half adder. A half adder can add only two single bit inputs and generate the output sum and the output carry. However, in digital systems, when we perform multi-bit binary addition, in that case, the carry generated from the previous stage should be included in this addition. For example, if we add 1 1 with 1 1, now here, first we need to consider the least significant bits. So, here we will perform 1 plus 1. So, sum will be 0 and the carry will be 1. Now, this generated input carry must be added to the next stage. So, now we have 1 plus 1 plus 1, 3 single bit inputs. But half adder can only take 2 single bit inputs. There is no provision to accept the incoming carry from the previous stage. And this requirement led us to the full adder. So what is full adder? Full adder is a combinational circuit that adds 3 single bit binary inputs. Just like a half adder, full adder is also a combinational circuit. And we all know what are combinational circuits. Circuits whose outputs entirely depends on present input values. So, full adder is a combinational circuit because the output sum and the output carry only depend on the present input bits that we are adding. And full adder adds 3 single bit binary inputs. And out of these 3 single bit binary inputs, one input is the input carry from the previous stage. And just like any other adder, full adder generates two outputs, sum and output carry. So, full adder generates two outputs, sum and Cout. Here Cout means output carry or the final carry. So, I hope you understand what is a full adder. Now, let's see its truth table. Here we are having three inputs, A, B, the two single bit numbers that we want to add. Cin is the input carry from the previous stage and it generates two outputs, sum and Cout. Now here we are having three inputs, which means we will have 2 to the power 3, which is equal to 8 input combinations. So here we are having the 8 input combinations and their respective output values. Let's verify few of the combinations. Let's verify the first combination, 0, 0, 0. So here, 0 plus 0 will give sum 0 and carry will be 0. Now this sum 0 plus this 0 will give final sum 0 and final carry 0. Let's verify the second combination, 0, 0, 1. So 0 plus 0 will give sum 0 and carry will be 0. Now this sum 0 plus this 1 will give final sum 1 and final carry 0. Now let's verify this combination, 0, 1, 1. 0 plus 1 will give sum as 1 and carry will be 0. Now this sum 1 plus this 1 will give final sum 0 and final carry will be 1. Now let's verify the last combination, 1, 1, 1. 1 plus 1 will give sum 0 and carry will be 1. Now this sum 0 plus this 1, 0 plus 1 will give the final sum 1 and we already have the carry, which is our final carry 1. And similarly, you can verify the remaining combinations as well. So, I hope you understand the truth table of the full adder. Now, in order to construct the logic diagram of the full adder, we need the Boolean expressions for the outputs sum and cout. Let's consider the output sum. Focus on the combinations where output sum is equal to 1. Now, let's find their corresponding minterms. In this input combination, A is 0, therefore A complement, B is 0, therefore B complement, and Cin is 1, therefore we will directly take Cin. So, the minterm for this input combination is A complement, B complement, Cin. Now, the minterm for this input combination is A complement, B, Cin complement. The minterm for this input combination is A, B complement, Cin complement. And the minterm for this input combination is A, B, Cin. Now we will perform the OR operation between these four minterms to generate the Boolean expression for the output sum. So this is the Boolean expression for the output sum. Here sum is equal to A complement and B complement and Cin, or A complement and B and Cin complement, or A and B complement and Cin complement, or A and B and Cin. Now, in the first two terms, A complement is common, and in the last two terms, A is common. So, we will take A complement common from the first two terms and A common from the last two terms. Therefore, we will have this expression: A complement common from the first two terms, and we are left with B complement Cin, or B Cin complement, or A is common from the last two terms, so A, and we are left with B complement Cin complement, or B Cin. Now we already know B complement Cin or B Cin complement is equal to B XOR Cin, and B complement Cin complement or B Cin is equal to B XNOR Cin. And we all know B XNOR Cin is complement of B XOR Cin. So the expression will be A complement and B XOR Cin, or A and complement of B XOR Cin. Now to simplify it further, I will assume B XOR Cin as X. Therefore, complement of B XOR Cin will be X complement. So, the expression will be A complement and X, or A and X complement, which is again an XOR operation. So, this expression is equal to A XOR X. And what is X? X is B XOR Cin. So, the final expression for the output sum will be A XOR B XOR Cin. And similarly, we can find the Boolean expression for the output carry by considering the rows where Cout is equal to 1. And after simplifying the Boolean expression, we will get Cout as A and B, or B and Cin, or A and Cin. Now, we have derived the Boolean expressions for sum and Cout, which means now we can construct the logic diagram for the full adder. So, this is the logic diagram of the full adder. Here we are having the three inputs A, B, Cin, and two outputs sum and output carry. Let's quickly verify this logic diagram. The output of this XOR gate will be A XOR B. Now this output A XOR B is the input for this XOR gate, and the second input is input carry. So the output of this XOR gate will be A XOR B XOR Cin, which is the expression of our output sum. Now, this first AND gate will generate the output A and B. The output of this second AND gate is A and Cin, and the output of the third AND gate is B and Cin. Now these two OR gates are performing the OR operation between these three outputs. Therefore, Cout will be A and B, or B and C in, or A and C in, which means our logic diagram is absolutely correct. And I hope you understand this logic diagram. Now, let's implement the full adder in Vivado. But the question is, which modeling style should we use? If we use behavioral modeling, then we need to write the 8 input combinations using if-else-if statements. That will make our code very lengthy. If we use structural modeling, then first we need to create separate files for XOR gate, AND gate, and for OR gate. Then we need to create 2 instances for XOR gate, 3 instances for AND gate, and 2 instances for OR gate. Then with the help of port mapping, we need to connect them to create the full adder, which is again very lengthy. Now in data flow modeling, we just need to write the Boolean expressions that we have already derived, which means data flow modeling is the suitable choice for the implementation of this full adder. So let's implement the full adder using data flow modeling in Vivado. So let's go to my laptop. So we are in Vivado's code editor, and here I am starting the code by importing IEEE library along with the standard logic package from the IEEE library. After library declaration, we have the entity block. Here I am naming the entity as full_adder because we are implementing full adder is port. Now inside the port declaration, I have declared all the input ports and all the output ports of the full adder. The 3 input ports A, B, C in, and 2 output ports sum and Cout, and all of them are of standard logic data type. After port declaration, we can end this entity with the keyword end and the name of the entity full_adder. After entity declaration, we have the most important block, the architecture, starting with the keyword architecture, and here I am naming this architecture as data flow because we are using data flow modeling code of entity full adder is. Now inside the architecture, after the keyword begin, we will write the Boolean expressions for output sum and for output carry. Now what is the Boolean expression for the output sum? Sum is equal to A XOR B XOR C in. Now what about the output carry? Cout is equal to A and B, or B and C in, or A and C in. So after the keyword begin, we will directly write these two Boolean expressions. So here I will write output sum is assigned as A space XOR space B. Now why I am using this space? So Vivado can easily detect this XOR operator. Similarly, space XOR C in semicolon to end the statement. Now I will write the Boolean expression for the output carry. Cout is assigned as. Now for Cout, first I will write all 3 AND operations before the OR operations. So I will use parenthesis to perform the AND operations first, then we will perform the OR operations between them. So inside the parenthesis, I will write A and B. Then the second AND operation inside the parenthesis, B and C in. Then the third AND operation inside the parenthesis, A and C in. Now, between these 3 AND operations, we will perform the OR operation. So, I will move my cursor at this point and I will write OR to perform the OR operation. Similarly, here I will write OR and semicolon to end the statement. So, here we are done with the Boolean expressions inside the architecture. And I hope you understand the data flow modeling code for the full adder. Now, let me save my file first. Now, after saving this file, let's see the schematic diagram generated by Vivado. For that, go to RTL analysis, click Open Elaborated Design and select Schematic. So this is our schematic diagram generated by Vivado for the data flow modeling code that we have written. On the left hand side, we have the three inputs A, B, C in, and on the right hand side, we have the two outputs sum and output carry as C out. And here we can clearly see we are having two XOR gates, three AND gates, and two OR gates. Over here, this XOR gate is performing A XOR B. So, the output A XOR B is the input of this XOR gate and the second input is C in. So, the final output will be A XOR B XOR C in, which is our output sum. And these three AND gates are performing the AND operations between the three inputs A, B, C in. And these two OR gates are performing the OR operation between the outputs generated by these three AND gates. So, the final C out will be A and B or B and C in or A and C in. So here, using data flow modeling code, Vivado directly converted the Boolean expressions to the schematic diagram. So, I hope you understand this schematic diagram. Now, to verify our VHDL code, let's see the simulation waveforms. For that, go to Simulation, click Run Simulation and select Run Behavioral Simulation. This will take some time, so wait for a few seconds. So this is our simulation waveform window. Here we are having our three inputs A, B, C in and two outputs sum and C out. Let me quickly assign all the 8 input combinations to these three inputs so we can verify our VHDL code using force constant. So here I have assigned all the 8 input combinations and the waveforms are generated. Let me maximize them. Let me zoom in further for better visibility. So this is the waveform for the input A. This is the waveform for input B. This is the waveform for input C in, and these two are the waveforms for the two outputs sum and C out. Let's verify the same 4 input combinations that we have verified in the presentation. The first input combination, the second input combination, the fourth input combination, and the last input combination. So, the first input combination, when all three inputs are equal to 0. Here, sum is 0 and final carry is 0, which is absolutely correct. In the second input combination, when A is 0, B is 0 and C in is equal to 1, then sum is 1 and final carry is 0, which is correct. In the fourth input combination, when A is 0, B is 1 and C in is 1. Here we are getting sum as 0 and final carry as 1, which is correct. And in the last combination, when all three inputs are equal to 1, here we are getting sum as 1 and carry as 1, which means our VHDL code is absolutely correct. So, I hope you understand the data flow modeling code for the full adder along with its schematic and the simulation waveforms. So, in this way, we are done with the full adder and its implementation using data flow modeling. With that, we are done with the topic of full adder using VHDL. And in the next lecture, we will implement our next combinational circuit, which means we are done with this lecture. I will see you in the next one. Thank you.